pulse rate, see, usually these are DC beams, but you can have it pulsed, but still every pulse have a bunch of ions, right? So the problem is still there. And see, the event trigger you can get by 3 different ways. Either it is a pulsed ion beam or a pulsed extraction field you can do. So you just pulse the extraction field, that you take it as event by event. Or the other part is that every dissociation will have an electron ejected in a separate detector. So you can use 3 kinds of event trigger, and time of flight to the detector is measured with respect to this event trigger. Now for this time of flight measurement with a laser, it is easier, because if the laser is pulsed, you can get a trigger from the laser oscillator, okay, or after the amplifier, say 1 kilohertz or 2 kilohertz. But for the ions it is not possible unless you pulse the ion. Now, pulsing an ion beam is not very trivial job. People have done that. They sometimes have a parallel plate and they just sweep the parallel plate with a slit, and that cuts over whatever comes out. The nuclear physics will bunch them. Bunching is a radio frequency thing. It's a lot of hard work there, where in every bunch you have huge number of ions. And that also creates problem, because at every interaction you get a flush of molecules. Okay, so there are ways people try to do at different experiments. Electron is the most preferred, but I won't say electron is the most preferred, because you can also have charge exchanged ions. Charge exchanged ions. So I tell you what is the problem about electron and charge exchange ions. So, yeah. So when I will explain this schematic, I will just come to that point. So this is some kind of a schematic of a collision setup. So you have your projectile ions coming from, okay, I did it with ECR source, but any source will do. So any charge source will do. So the projectile ion comes from this direction, it interacts at the center of this time of flight. Now you see, this is a time of flight where one side you extract the fragments. So you can call it as fragment time of flight mass spectrometer. The other direction is electron time of flight, because the electron has to go to the other direction. This electron comes so fast, means it probably reaches at like tens of nanoseconds, that even if this electron has a structure, energy structure to it, you cannot really separate it out in that very small distance. So this is only good that you get a trigger. It just starts. First electron comes, it just gives you a start, and after the start the fragments are heavier, much more heavier. Even the proton is 2000 times heavier, so the fragments will reach here at a much later time. Okay, so electron can be safely triggered, but electron trigger and time of flight has its own problem. That is, if you have a highly charged ion, if you have a bigger molecule, you will knock out a lot more electrons. Okay, so if you knock out a lot more electrons and you excite your ions, you excite your molecule to higher charge states or higher, okay, since the electron, depending upon the easy way of getting electron, then it will modify your fragmentation pattern. Just because if an ion is like 5 times excited, means 5 plus, you have 5 electrons to come out, and one of them is the first one that triggers it, gives you a time of flight. So when you see at the main time of flight feature, the higher charge states will be always bigger, a lot of higher charge states, rather than undissociated ion, molecular ion. Okay, if I can show you I don't know whether I have that picture, but yeah. I'll come to that. Exactly. I'll come to the last stage that yeah. So the slowing down, you can slow down the electrons by what he said is that by having a magnetic field. Okay. Okay, yeah. So yes, what he said is right. You can slow down the electrons by increasing their path length. it's just a trigger. But yes, what he said is right. You can have a magnetic field. So you can have, so in the last slide I will actually have that picture. So you can have this a magnetic field across this entire time of flight mass spectrometer. When you have a magnetic field, the electron does not just run here. The electron takes a spiral path, and that increases the time of flight. And when you collect those electrons, because the time of flight of the electron is increased due to the spiral path, then the electrons, you can resolve the energy for the electrons. Now, one thing, it's a technical part, but you have to take care, is that what is the amount of magnetic field you should put. So the electrons, it's not only one electron. You see the electrons are coming out in every direction, right? So it will have nodal structures. So don't put a magnetic field, or don't put a magnetic field such that you are hitting at a node. So you either hit at the, not at the node, but if you need like the entire energy spectrum of the electron, collect all of them, both position as well as time. So you have to have as much nodes, as well as then you have to sit on complete antinode, right? Then you can get the entire picture on your position sensitive detector, and you can resolve in time the electron energy. Yeah. Yeah, it's like if you're doing a complete experiment where you want to measure the momentum of all charge partners, like a helium. So the helium, or say the hydrogen, okay, it has the 2 protons and then the 2 electrons will come out. And if you want to detect all 4 of them, 2 will go on this side, which you have a position sensitive detector on this side. A similar position sensitive detector will be on the other side of it. Okay, and then but the ions you can separate out, but for the electron side, if you put a magnetic field along the direction of the time of flight, the electrons will have this cyclotron motion, and these are 2 electrons and you catch both of them at 2 different energies or similar energies, and from that you get all 4 body and a complete quantum picture. You can have the complete dissociation picture of what is the momentum taken by each partner, including the electron. Okay, this is a very important part, that why cold trips became a very important tool in these sort of studies, in complete fragmentation studies. The other thing is that not only the electron you can use as a trigger, you can use the projectile ion as a trigger. So as I told you, that if the projectile ion is highly charged, so it is like argon 8 plus or 9 plus, whenever it, and this is your gas jet, so this is your molecular jet. So you dissociate them, and the fragments are moving in this direction because of the electric field is in this direction, and you collect the time of flight with square root of m by q, and not only the time of flight, you also detect the position x, y and t. But due to this projectile ion, what happens is that it collects, since the outer shell of electrons are loosely bound, so the projectile is highly charged, means it's devoid of electrons, so it will collect a number of electrons from there. And then if it collects 1 electron, say if you start with argon 8 plus, you will the fragment other than argon 8 plus, the projectile will now become argon 7 plus. Or if you collect 2 electrons, argon 6 plus. And then you separate those ions in an electrostatic analyzer, and you can detect either argon 7 plus or argon 6 plus, all of them by either one detector, or you can image them one by one. So you can collect one single electron capture, double electron capture. The goodness is, if you are collecting a single electron capture and you are using as a trigger of argon 7 plus, so the molecule has only only lost one electron, means it given away one electron. So your undissociated molecular ions or the lower fragments will be recorded in a much better way. You will have I mean your detection of those ions will be a lot better than detecting electrons, because the electrons means the more you have dissociated, more you have released electrons, the electron trigger probability goes high. But here it doesn't depend upon how many electrons you have released. You just have one electron capture from the molecule. So if you want to look at, say, single ionized species, means the entire molecular structure is there, you just have one electron loss or just two electron loss, and see whether that molecular structure has a metastable state or not, so that the entire molecular structure, even in highly charged state, it is stable or not, whether any bonds are broken or not. That is possible if you really have a single electron capture. So it does not depend upon how many electron you release. Now, problem, yeah. This could be an inertial. You can. Yes. Yes, that you can know. I mean, see, in a highly charged ion or in an ion collision, what is the problem is that you have all the opportunities open. So you cannot really control that I only need a single collision or a single ionization or a double ionization. In laser, you can change the intensity and you can somewhat control that I need a single or a double ionization. Okay. But in ions, because the impact parameter is widely ranged, you do not have a control on that. So it's not that if you just I want only my nascent single molecular frame. You cannot. It will open you all opportunities. Okay. Now if you are having an electron trigger, because electrons are more formed due to multiply charged molecule, one of those electrons will be most probably you will get. So instead of having an undissociated peak of the molecular fragment, you will get the fragments more. Okay, not the molecular parent ion. But for a single capture, if you have only single capture, you know that this projectile has only captured one single ion, one single electron, and became argon 7 plus. So you have a much better chance of looking at the time of flight where you have undissociated molecules. So therefore the electron trigger and the charge exchange projectile trigger both become so important. Then you probably have to do the electron spectroscopy. Yeah. So yeah. And then you can have not only single capture, you can have double capture. So yes, I jumped into the fact, but so for the others, you probably have already understood that this is a cross beam experiment where this is the molecular beam and this is the ion beam arrangement. So this is a molecular beam and the projectile beam crosses at perpendicular to each other. The electric field is there to extract the ions and transport them through the detector. Time of flight to the detector is measured with respect to the event trigger, which we discussed quite a lot, that either it can be electron or it can be charge exchange projectiles. And another important, the fast response detector to record successive ion arrival. This is important, that when you have this position sensitive detector, see how many events, or how many actually what you can say, how many records have you done. See, one will be the time of flight, but then you can get two more things. That is, if this is your x-axis, this is your z-axis, you also need the x and y. Remember this picture, when the molecule dissociates, the molecule is dissociating because it has an internal energy, right? The molecule is dissociating and the fragments will go on all three directions. So once you can detect all three, the time of flight, but the time of flight will give you only one momentum axis, not the other two. So you need to have the x and y to get the complete picture of the other momentum axis. Then only you can reconstruct back with this full 3D momentum, you can reconstruct back what is its structure during dissociation. Okay. So we usually use this position sensitive detector, and this is a basic time of flight that you get. So you see, this is a 1.2 MeV argon 8 plus dissociating with nitrogen, but the trigger with the electron. And you see here that this is a time of flight that you get. So even with the time of flight, what information we can get? So your time depends upon this MQ, the parallel momentum and electric fields and other dimensions. And so with this spread, you see there is a forward and backward spread to that. So you see here, this is an undissociated nitrogen molecular ion. This is doubly charged undissociated molecular ion. But then there are also events where we have detected like nitrogen going backward and forward. So this is a diatomic molecule. What does it mean by going backward and forward? You just go to this guy. Here, what I was explaining. So you have a nitrogen breaking apart, and what happens is that one nitrogen fragment going in this direction and the other fragment has to go to the opposite direction and turn around. So it takes longer time. This is exactly shown here, that every nitrogen fragment, this is nitrogen 4 plus or nitrogen 3 plus, you have a forward and backward. Right? So even with this forward and backward, you can have an idea of what is your kinetic energy release in this way. So see here, this does not have just one peak. So there is one peak and there is also a shoulder to this. So does it depend from only one fragmentation or two fragmentation? Are these fragments nitrogen 1 plus and 2 plus correlated or not? These things we cannot get from just a time of flight. Right? You might have that, is it only nitrogen plus which is forming, not nitrogen plus and nitrogen 2 plus. But there is no way to get from a time of flight spectrum whether they are formed or not, although you see that there are two different energies over here. This gives you to the next level of complication, or next level of detection method, which is called like coincidence momentum imaging. So this I was telling from the first time, why do you need event by event? Okay, a single molecule breaking and detecting every molecular fragment, because what you need at the final end of the day is a coincidence momentum imaging. To get a complete kinematic information about the fragmentation dynamics, we need angular information between every coincidence partner. So how can you do that? This is like record all ions from a single breakup event. So see, like ABC is the molecule, triatomic one, and then after collision it becomes ABCN plus with a lot of N electrons. And then this ABC, this molecular ion breaks into say A, B and C. Right? And now to get, since this triatomic molecule breaks up into fragments, unless I detect all these fragments for a single molecular breakup, I cannot get a complete momentum, a complete dynamic picture. So what we do here is that we start with the we what we do here is that we start with one trigger, and then at every time axis or every detection axis, position, both position and time, we detect one fragment one after the other. So the one with lower mass will come first, and the one with the higher mass will come second. Right? So if you take a molecule like OCS, it's a linear molecule OCS, it has different masses. So is ABC may be OCS, and OCS breaks apart either O plus, C plus, and S double plus. It can be all different possibilities. So to get this, whether this linear molecule stays linear or not, whether it breaks one after the other or not, you have to detect all the fragments. But from a single molecular event, you cannot have O from one molecule and C from the other molecule. Then they are not correlated. Okay. So for every channel, detection channel, you need to detect from AB, detect A and B, and from ABC, A, B, and C. Okay. This is a sequential detection. This is called multi-hit. Okay, multi-hit means for one trigger, you wait for multiple fragments to arrive and you record all of them in sequence of time. Okay, so this is what it means is that. Yeah. What exactly we do is that, like, I will show you a data where it is C2I2. So iodine has a huge mass and carbon has very low mass. So you can simulate this just by calculations. Okay, that what should be my, with the electric field that I have given, what should be my maximum time to reach, and then you fix your electronics so that this is a start and this is a stop. So my stop should at least be beyond of that time. So at least iodine plus or C2I2 plus, that is the biggest mass that I am going to record, my stop should be beyond that. So I'm not missing any fragment. The longest time of flight, that depends upon time to digital converter, and it can be like one I had is 32 microseconds. Now see, there's a tricky part that for a time of flight, the longer you go, the better mass resolution you get. So for MALDI kind of thing, which the biologists do, they use protein masses. So they only singly ionize, but they have a multiple reflectron kind of arrangement where you reflect the masses back and forth, so you increase the path, and increasing the path will increase your delta m by m, your mass resolution. Mhm. Yeah, the T and the spread of T. Mm. Mhm. Longer the T means the flight path is more. Uh, s- Now that is because see if you go to this picture, if you go to this picture, what defines your see the every mass if it does not have its own energy, every mass that is m by q that is formed will have a drift tube length, okay, while reaching, and the one factor that works against it is your spread of the initial thing. So if you go to a lot more, so if your time of flight has changed, but you have your minimum spread, then I guess you should have a better resolution. Mm-hmm. Dead time, what do you mean by dead time here? In the drift tube, exactly. Yes, yes. Because these two fields are actually adjusting itself to drag it, and then it is the flight path. I think there is a factor of two kind of thing it was there. T square. Okay. Now his question comes is that if you have a longer t, will that 32 microsecond will be enough for higher masses if you go to, so then you have to have a time to digital converter which will longer range. Yeah, yeah. Yeah, but see, we for our case, it is not just the time of flight that we are looking. We are also looking at this x and y. So we cannot really, if you have a longer time of flight, your detector has to be wide enough that it catches the, so the molecule which is breaking away this way will reach the edge of the detector. Maximum in my life I've used like 120. That's not in India also. So I used a 120 in Japan and that's the biggest one. I'm fighting with IUAC that at least put an 80. They are still stuck with my PhD 40. Yeah, it's the price, it's the arrangement, but yeah, bigger detector anyway increases. It's the same for the VMI also. Bigger detector will give you a resolution in energy, better resolution in energy. Okay, so yeah, from time of flight, we do need coincidence momentum imaging for each ion, each event, and then record T, X, and Y. Repeat for several events. That is means you have a list mode. So you have event by event. You gather and put up. I mean your statistics, and then transform this X Y to PX, PZ, PY for all ions for each fragmentation. And then from the pattern itself, you can get some slopes. So I can tell you like one slope over here.